Hello and welcome back to another episode of Math with Stone. Today we're going to be doing a force and a power and an energy problem on an incline, okay? So this first thing we got going on, we got a motor and it's raising a log because I don't want to raise a log by hand. And it's got an angle of 14 degrees and it is apparently going to raise it probably 10 meters, all right? So the motor drags up that log that has a mass of 452 kilograms. Show that the component of the weight of the log acting down the slope is 1070. Okay, so the component of the weight acting down the slope. So that sounds like we want the force parallel on a slope, which is equal to mg sine theta. All right, so let's make sure that actually is it. So let's see, m times g times sine theta is equal to the force parallel. So let's see if 1070 does in fact equal 452 times 9.81 times sine of 14. And if it does, then we're golden and we got our answer. It's only 1 point, so I doubt it's going to be anything too complex. So let's do 452 times 9.81 times sine of 14. And we get 1072. So that is correct. So this works out because according to sig figs, apparently we only have 2 sig figs here and 3 sig figs there. It's going to round appropriately, or it's close enough. A lot of times on these show, they don't give you the exact number because they don't want you to be able to guess and check to it. Okay? So the log starts at rest. A constant frictional force of 525 newtons acts on the log. The log accelerates up the slope at 0.13 meters per second squared. Calculate the tension in the cable. So there's maybe a few different ways to do this, but I'm going to start with sum of all forces. Okay? So sum of all forces will equal MA. We got the weight that the log is having to fight. So the weight that the log is having to fight is going, we're going to do a free body diagram. We got the weight going down the incline would be that way. The friction opposing the motion would also be that way. Okay? And then the tension pulling it up would be the other direction. And the tension is actually going to be bigger than those two things combined because it's going up the incline. It's actually accelerating up. So we have tension winning, which I drew as a torque. Tension is just a regular T, force of tension, minus the 1070 that we just had. That would be the force of gravity parallel, minus the force of friction, 525, would equal MA. 452 was the mass from up at the top. You can't see it. It's off screen. Times A. All right. Well, A is equal to, I could have plugged that in, 0.13. So we're just going to solve. Tension would equal 452 times 0.13 plus the 1070 plus the 525. It's going to be more than everything else because tension won. So we just got to do the math for that. And when we do the math for that, we end up getting around 650, or you could give you a more precise answer of 1653.76 newtons, both of which would have been accepted according to ACE. Okay? Next, we got the log is initially at rest at point S. So point S is the bottom. So it's originally at rest at the bottom. It is pulled through a distance of 10 meters, according to the diagram as well. Calculate for the log the time it takes to get from S to P. This just seems like a kinematics question, okay? So it went a distance of 10 meters up here. It had an acceleration, according to the problem, of 0.13 meters per second squared. And it's had an initial velocity of 0 meters per second. Okay? I think that's enough to just do the problem. Let's see. We got delta x is equal to vi times t plus 1/2 at squared. That's the equation. I got it right first try. Our delta x would be 10. Our initial speed would be 0, so we can plug in 0 if we want to, but we don't have to. 1/2 times 0.13 t squared, and we just solve. So we end up getting 0.13 times 0.5 is 0.065 t squared. is equal to 10. Divide 10 by 0.065, and you get 153.84 is equal to t squared. When you square root that, you get 12.4 seconds. So let's make sure it is correct on the answer key. 12.4 seconds. And that's a two-pointer. Normally the two-pointers are questions where you have to just plug it into an equation and solve. If it's a three-pointer, you normally have to use two equations. So that gives you a clue as to how many steps you're going to have to do. Find the magnitude of the velocity at point P. Well, at point P, that is after the 10 meters has gone by. So this time, here's our third point. We're going to need to use V final is equal to V initial plus AT. That is one option of a formula, but there are plenty more. You could even do like sum of all forces is equal to MV final minus MV initial, which I'm kind of wanting to do that. Force times distance is equal to change in energy. That's one option. Then that would be your force, which we found out from the previous problem, the force of tension, the 1650, times the distance of 10 would equal 1/2 mv final squared minus 1/2 mv initial squared. That would be one option, but it is by far the longer of the two options. But then you wouldn't have had to get the time correct. So it depends on which part you feel like more confident with. The other option you could do is if you did force times time, that would equal your change in momentum, which means that it would be force times time would equal mv final minus mv initial, if you couldn't remember, this formula. All of these would end up working, okay? All of these. I am going to choose to use the easiest of the options after doing many of them. V final is equal to V initial plus A times T. V final is what we're looking for. V initial was 0. A was told to us originally A was 0.13 times time, which was 12.4. So we just multiply those two. 0.13 times 12.4 is 1.612 meters per second. And I do not feel like we would need all of those, so I'm going to scribble out that too. We don't need all those sig figs. All right. The cable breaks when the log reaches point P, which, oh man, that's sad news. So the cable broke. When the cable breaks, it's going to go back down. Okay, so when it goes back down, sketch the variation with velocity versus time of the log. So we got to think about here. When it breaks, the log is going to go back this way, and that is going to go back with a force that was told from number 1 of 1070 newtons minus the force due to friction, which would be 525. Which means that when we subtract those two, you get virtually the same answer. 1070 minus 525 is almost 525. 1070 minus 525. This is going to have an acceleration of 545 down the slope. Okay? And if it has a constant acceleration, that means that the velocity graph is going to be constant as well. Okay? Do we need to make sure that this is a velocity? Yes, it's not a magnitude question, so it is going to have a slope of 545, and I believe it should be negative 545. It starts out with 0 velocity. I disagree with that. Let's manage chord breaks. Sketch the variation velocity versus time, starting at S until it returns to S. So now we actually have to be careful. So we want the whole velocity versus time. Originally, it was going up, and then it broke, and then it went back down, okay? And when it breaks, it's going to continue to go up for a little bit longer. So that's an important detail. The log is going up. It accelerates upward. And because it has a velocity at point P when it breaks, it's going to continue to go upward a little bit longer, and then it's going to come back down. So velocity is going to increase. It's going to increase originally with the acceleration of 0.13 meters per second. So that would be the slope. So it's going to go up at 0.13 meters per second. I messed up when I said this is the acceleration. It would be equal ma. So we are going to have to be very aware of that. At a time of t, sketch for time of t. I want to know when it. I'm just going to do the problem that I want. It's going to go up, and this is going to be an acceleration of 0.13, which means the slope is, this would be up by 0.13, and over this would be 1 second. And then it had a total time of 12 seconds. So at 12 seconds, we'd be at a much faster velocity. We'd be all the way up here at 1.6. All right. After it broke, it continued to go up. But as it continued to go up, it would still have a positive velocity. And then eventually, it is going to have a negative velocity. And that negative velocity would occur at a specific time. We're not asked to find when it occurs, but it would have a negative velocity once it starts going back down the hill. All right, it will continue to go up the hill that is represented by this portion right here, and the slope would be consistent this whole time. All right, so it'd go up and then it would go down, and it would be consistent slope, not a curvy slope. If we divide by the mass would be 452. So 545 divided by 452 ends up being a slope of 1.2. So this slope should technically be steeper. Depending on, I don't think I spelled, that's stepper, steeper. So depending on how many points this question was worth, it was worth 4 points. You might have to be more precise. It says, straight line from the origin, line down to 0 velocity in the short time compared to stage 1. So this should be a shorter time than stage 1, so it should have been steeper. I already committed in pen, so I was over. Less steep line, negative gradient, final velocity, then of at least 2 times. So a lot of things happening here. I don't want to read it to you. You can read it yourself if you would like to. I am ready to cook dinner. It is 6:30 at night, and I am hungry. Thank you for joining me. I will talk to you later. Bye.